Hello and welcome to the practical part of my presentation. I have done some setup before starting the record. So here you can see the user interface of the Saleae Logic analyzer. I have connected these first three signals to the UART interface, which is present on the ACRIOS and WD board, and those two specific signals are showing communication between narrowband IoT module and the microcontroller. Last four signals are SPI communication between the radio chip and the microcontroller. Okay, so let's start by starting record of the power analysis. Here we can see real-time consumption of the device. As the power is not enabled, the consumption is close to 0 ampere or nano ampere. Now I will turn on the power, and I will also start a record of the signals here. Quite interesting thing is that you can enable this console view. So if you capture, for example, UART signals using Saleae Logic, you can see it in the form of a console, which is very handy and quite good to see what is actually happening. I will not show how UART can be synchronized with OTII Qoitech, but this is also very handy, so that you can see at what happens and what consumption is when the thing happens. How did I configure the device? You can see on the video on the upper right side, I preset it so that it receives this specific meter, and it should keep attempting to receive this meter. Yeah. And what we will check first is that the power consumption of the device, which is now close to 0 because it is in the sleep mode, just the narrowband IoT module is talking to the network, but it will go to sleep after a while as well. We can see that based on the power consumption, you see what is happening with the device. Now the device woke up, and you can see that the power consumption got up, and now the reception in T1 mode, wireless M-bus T1 mode, was enabled. You can see that from time to time the microcontroller talks to the radio. You can see it here. I didn't show the SPI communication in the console because it would break readability. Okay, and what you could see, okay, I'll stop it now. I'll stop the record. And what you could see here is that after a while, the device received the heat cost allocator, which is using wireless M-bus, and here it read out what the heat cost allocator transmitted. Here you can see that it is going to send the data to narrowband IoT, and what we will check, we can check, for example, is at what frequency did this reception happen. Let's imagine it is not wireless M-bus, but let's imagine it is some proprietary protocol. So let's check at what frequency it happens. I have already checked before. Let's imagine this is not our device, the green board, but it's some foreign device. So I have already checked what's the chipset there, and I have prepared the data sheet, which is this SX1261, and the command to see to set the frequency has opcode 86. So let's check. Let's check if we will find here the opcode 86. So I will switch to data table view, and I already entered here the filter for 86. And if I go here, because this is the right direction I'm looking for, now I will scroll. So I will scroll first, scroll in, and then I will tell him jump me to where 86 is sent to the device. So this command is setting the frequency which should be used for reception. And here we can see 36.4F35.8E. So I will do some little math based on what the datasheet tells us, and based on the value of the crystal, which we can measure also using an oscilloscope, or which we can guess based on what's written on the package. And it is said that the R frequency is equal to what is sent there over SPI. So I will write it in hexadecimal: 36 for F 35.8E. Yeah, like this it is 911 million. So this is not the frequency, because we know that the frequency is wireless and bus T1 mode, so this is not the right one. It should fall somewhere in the 868 band. So I will multiply it by 32 million, 32 megahertz, and divide according to the equation to 2 to the power of 25, and it gives me exactly 868 megahertz, 950 kilohertz. So this shows how using Saleae Logic you can using the datasheet of the radio chip you see there, you can learn what's the frequency used for transmission. If we would go deeper in the analysis, we could, for example, try to find this data, the data of the wireless and bus frame are starting here, because, well, we know it because it's our device. But what we could do, for example, is we could look in this analysis to the command where the FIFO of the receiver is being read out, and then we could read out of the FIFO this data. We would not read it in a raw format like this, because it's wireless and bus T1 mode, so there is some encoding which we would have to apply, and there is too little time here to really go through this. But this would be the approach we would use. Also, I will explain why I'm showing here the SDR. This is the 868950 frequency, which we could see that was set by the receiver, and you can see that every time there is a peak here, which means some wireless and bus meter transmitted data, and of course the device has to be in the receive mode at the time. So when a transmission happens and the receiver is the device, the ACRIOS converter is receiving, it will get the data, and you can see it on the power profile. So we can correlate what you see on the SDR with the power profile and with the Saleae Logic. So you can see all three things work together and give you the overall picture of what's happening in the system. Okay, so I hope you enjoyed this short presentation how Saleae Logic, OTII Qoitech, and SDR can be used to analyze a system. I didn't go deep, but you can already imagine how this can be used. So thank you, and now I will continue the presentation.